Hello friends, today we are going to discuss about phase space trajectory. It is a most important part of CSIR net. Now first, what is a phase space? It's just coordinate plus momentum space is called phase space. We get a relation between momentum and its coordinate and it will give us a curve that is phase space trajectory. And it shows the relation between momentum and coordinate of any object under some potential that will be a constant or variable. So phase space trajectory, it shows momentum of system varies with coordinates. Now phase space lines can be easily drawn by using steps. So first is, if Hamiltonian does not contain time explicitly, then phase space lines do not intersect. Or if energy is conserved, then phase space lines do not intersect. The Hamiltonian is equal to Px square upon 2m plus potential, that is V of x, that is equal to total energy constant. So then Px will increase, Vx decrease. These are conditions when Vx is increased, momentum is decreased, and if potential is decreased, momentum will be increase, and if Vx turn to infinity, momentum that will 0, and if potential will 0, in that case momentum not be 0 but it has some certain value that is not equal to 0. On the other hand, if potential is minus infinity, momentum will be infinity. These are conditions. And if momentum is positive, then arrow on a phase space line will turn toward positive axis. And if it is a negative, the arrow towards negative x direction. That is look like that. If potential is positive, it will turn into positive x direction, and if it is a negative, it will turn into negative side. That is again some example according to it. And if there is a potential well, there will be some closed line phase space trajectory near the wells. Harmonic oscillator half kx square, that is look like that, and inverted harmonic oscillation minus half kx square, it will turn into negative side. And if there is a no potential well, then there will be not any closed line in phase space trajectory. So in one dimension, Fx equal to minus dV upon dx and V equal to potential energy, the slope of potential versus x graph, that is when it is a positive, it will turn into, and if theta is greater, then it will turn into opposite. In the first case, phase space line of harmonic oscillator, that is Hamiltonian equal to Px square upon 2m plus half kx square, that is equal to total energy, and it will be constant. Now the phase space line of above x-axis will be mirror image of phase space line below x-axis, that is look like that, and it is a mirror image below x-axis. The second is, if potential is symmetric, potential contain only even power of x, then phase space lines are symmetric about momentum axis. Now we take one example of GATE 2018. The question is, an inelastic ball of mass m has been thrown vertically upward from the ground at z equal to 0, and the initial kinetic energy of ball is E. The phase space trajectory of the ball is. So solution is, we have one surface that is equal to 0, and in an elastic ball we throw it, it gets some certain height, it has some maximum potential, and at a certain height velocity will be 0 and it will come back. In that case we have potential equal to mgz, that is a z coordinate. Now we have a graph between potential and coordinate z, and the graph is linear in between potential and coordinate. Now we have an energy that is equal to pz square upon 2m plus v of z. When it is a constant, the potential will be 0. In that case, when potential is 0, our momentum get some certain value that is not equal to 0. And in graph, potential and in coordinate, when potential is 0, the momentum has some certain value, and when potential is varies with coordinate, and potential is increase with coordinate, potential is increase, momentum will be decrease, and it turn into decrease in coordinate side. And in symmetric case, it's same in below side. And in a question, the question is, in elastic ball, when the ball goes upside, it will turn into back and get some certain value and certain height, and again potential has decreased and it has some certain value. Look as it, and it is a phase space trajectory in between momentum and coordinate. One phase space trajectory questions. Draw a phase space line for the potential shown in the figure. The figure is a given and we draw the phase space line according to given diagram. We draw the lines of momentum and coordinate, and it is a potential well, and it is infinite potential well. So according to a line, we create a mirror image of the phase space in between momentum and coordinate. We join the lines here. Momentum is 0, And further, we draw all the lines here. It is look like that, and we start from the lines x side. We said particle moves inside the trajectory or force on the trajectory inward negative. Second case, how to plot a potential when its mathematical expression is given. For first step, find the point where potential is 0 by putting Vx equal to 0, find x. And in second step, find the point where potential is extremum. It is by dv upon dx, x equal to x naught, find x naught, and check maximum and minimum. For maximum, d square v upon dx square less than 0, and for minimum greater than 0. After that, show all point x and x naught in x-axis and connect the point where potential is 0 by making appropriate maximum and minimum. For maximum and 0 coincides, it look as it, and for minima and 0 coincide, the graph between potential and coordinate, it look like as. Now we take one example which is from CSIR 2015. The question is potential equal to minus half x square plus 1 upon 4 x to the power 4. A particle is moving in potential. Draw its phase space trajectory. The solution is v of x equal to minus half x square plus 1 upon 4 x to the power 4. In first case, we put v of x equal to 0. The value of vx is minus half x square plus 1 upon 4 x to the power 4 equal to 0. 1 upon 2 and x square common from the equation, and in bracket minus 1 plus half x square equal to 0. Half x square, it is minus 2 plus x square upon 2 equal to 0. The value of x is 0 and plus minus under root 2. And for find the point where potential is extremum, in that case derivative of v upon dx for x equal to x naught equal to 0. We put the value after derivative x naught plus x naught to power q equal to 0. The value of x naught is 0 and plus minus 1. And double derivative of potential x equal to x naught, it is After derivative we get minus 1 plus 3 x naught square. Put x naught equal to plus minus 1 and the value of its minus 1 plus 2 into 1 square. Minus 1 and plus 2 is 1. X naught is maximum at 0 and minimum at plus minus 1. Now we draw the trajectory according to this information. The value of x coordinate is this and this. We draw the phase space. This is coordinate x and it is potential. We take a point that is 1 and minus 1 under root 2 and minus under root 2. We draw it as we draw this symmetrical line downward. Here potential is decreased. Plus minus under root 2 is minimum value. So phase space trajectory will not be symmetric. The third case is the phase space line of a particle falling under gravity. In this case, we must define as potential equal to mgx. Now for a small oscillation, theta is small and v of theta equal to minus mgl into 1 minus theta square upon 2. We open the bracket, then we get minus mgl plus half mgl theta square. In this case, phase space trajectory is circular. Now for a simple pendulum, in initial condition, in case of no damping, the phase space trajectory is oval shape. And for a damping, phase space trajectory is spiral inward. The next question is, a particle move in one dimension in a potential equal to minus k square f to power 4 plus omega square x square, where k and omega are constant. Which of the following curve best describe the trajectory of the system in phase space? This question came in NET 2017. The solution is, now the potential is Vx equal to minus k square x to power 4 plus omega square x square. The first step is Vx equal to 0. The value of k square x to power 4 plus omega square x square equal to 0. So x is common from here and minus k square x square plus omega square equal to 0. X equal to 0 and x equal to plus minus omega upon k. Now the derivative of its b dash x equal to minus 4 k square x cube plus 2 omega square x. X is common from here, and minus 4 k square x square plus 2 omega square. Again x equal to 0 and minus 4 k square x square plus 2 omega square equal to 0. X square equal to omega square upon 2k square. The value of x equal to plus minus 1 upon under root 2 omega upon k. Now we are checking maxima and minima. Double derivative of potential equal to minus 12 k square x square plus 2 omega square. The double derivative of potential, that is equal to x equal to 0. Put the value of x 0, we get only 2 omega square, that is greater than 0. So x greater than 0 is minima. Now for maxima, x double derivative of potential x equal to plus minus 1 upon under root 2 omega upon k. Now put the value here, x square 1 upon under root 2 omega upon k. The answer is 12 k square upon 1 upon 2 omega square upon k square plus 2 omega square. The value of its minus 4 omega square, that is less than 0. So x equal to plus minus 1 upon under root 2 omega upon k is maxima. Now using this information, so first of all we create a graph in between potential and coordinate, that is potential and coordinate. Now we take a point where our maxima and minima making. Here first of all x equal to 0 and other value is minus omega upon k, and for maxima and minima, here our maxima and minima, the value of its 1 upon under root 2 omega upon k and 1 upon under root 2 omega upon k. Here it is a maxima and minima. Now we create a graph. Now when potential is 0, the momentum has certain value. We draw the lines. And other values is where potential is 0 and momentum has some values. And our B answer is matching for this phase space trajectory, and B is correct answer. Thanks for watching and subscribe for learning. Thank you.